Okay. Assume there is a capacitor and an inductor, and they're connected like this. Switch is open initially. When switch is open, obviously there's no current. But assume the capacitor is charged. Okay, let's say this plate is positively charged and this plate is negatively charged, with initial charge being Q naught. Fine. Now, some of you may have studied this already. Some of you may be looking at this for the first time. But tell me, what happens after we close the switch? What do you think will happen after we close the switch? See, what is an inductor actually? Rishi, what is an inductor?
Sir, it stores energy in the form of a magnetic
I'm
field.
asking, I know, I'm not asking what it does. What is an inductor? How do you make one?
Uh, you induce current in it.
Inductor is a coil, that's all. It's a conducting coil. Okay. It's a wire which has been wound like a coil, that's all. So answer this first, any of you. If there's a charged capacitor having a charge plus Q on one plate minus Q on the other, and you simply allow the plates to come into contact with each other. You connect the plates with a wire. What will happen? Forget about the inductor. Just capacitor, if you connect its plates, what happens?
Sir, will the voltage drop to zero?
Correct. The potential difference will become zero. And can you talk in terms of charge? What happens to these charges? One plate has positive charge, the other plate has negative charge. Now you are connecting them with a wire. What happens to these charges?
There won't be like it'll become zero.
They'll combine, obviously. Okay. Positive, negative. And how long do you think that will take? That process.
Sir, until it like
How long do you think it takes? Anyone? One plate having positive charge, another having negative charge. You simply provide a path for them to interact, come into contact with each other. What will happen? It will happen almost instantaneously. Okay. They'll neutralize. It will happen almost instantly. Within nanoseconds, it'll be finished. Okay. So what effectively happens is all the energy that was stored in the capacitor. See, when a capacitor is charged, there's an electric field between its plates. You know there is an energy stored in the capacitor. Okay, Q square by 2C. All that energy will get released. When the charges mix and neutralize, all the energy gets released. And that happens almost instantaneously. Very quickly it will happen. Okay. So a charge Q combining with a charge minus Q in a very short interval of time means in a very short interval of time, a significant amount of charge is flowing that will lead to a lot of current in this wire. Okay. A high amount of current in this wire. Usually it'll get burnt. Okay. But if there is a resistance, then current will, charge. If there is a resistance in the circuit, then charge will decrease slowly. And we had discussed that before, discharging of a capacitor, charging, discharging. Okay. So if there's no resistance and you simply connect the plates with a wire, they'll neutralize almost instantaneously, producing a lot of current, a high amount of current, which will usually burn the wire. Okay. Is this clear to all of you? Generally a spark, usually a spark also will get produced. I read this in a book actually. In earlier days, when there used to be these reel based cameras, okay, not digital cameras, reel based. Even in some digital cameras, even in DSLRs. Okay. Do you know how the camera flash works?
No, sir.
How does a camera flash work? Anyone? Okay. The camera flash has a capacitor in it. Fine. So the moment you switch on the camera, the capacitor gets charged. And when you press the shutter button and you want the flash, okay, when you press the shutter button, what happens? The two plates of the capacitor come into contact with each other. Okay, maybe not the plates exactly, but at least their charges are allowed to mix. Okay, and when that happens, a flash is released. That is what is flash. Okay, a light is released. That is what is flash. Okay. So if you allow the plates of a capacitor to come into contact, they'll neutralize instantaneously, giving out a spark or a flash. Now, think about this circuit, the second one. Inductor is a coil, we know that. It's a wire only, which is shaped like a spring. You are connecting it to a charged capacitor and closing the switch. So what will happen? The charges will try to combine. Okay, positive charge is on the left plate. Usually the direction of current is the direction of flow of positive charge. So positive charge goes this way, negative charge comes the other way. Or actually positive charge doesn't move, you all know that. Electrons go from negative plate to positive plate anti-clockwise. That means current flows clockwise. Okay. So you will see current flowing here. But tell me, in the presence of an inductor, can there be a sudden high current produced? Will an inductor allow that? If it's a plain wire, yes, a lot of current will get generated. That's okay. But if there's an inductor, can the current increase suddenly? Okay. Rishi, when I asked you what is an inductor, you were saying something in the beginning. What does an inductor do?
And it stores magnetic. Uh,
Energy. It stores magnetic
yeah.
energy. Okay. What else does an inductor do? Others also. Isha, Pradyun, answer.
So it basically stores it when there's like an electric field going through it. So
Not electric field, magnetic field. It stores energy in the magnetic field. No?
yeah, sir. Yeah.
Ha. Okay. What else does an inductor do?
Opposes sudden change in current.
Good, good. Inductor opposes sudden changes in current. Okay. That induced EMF will be there. No, see, inductor, the name itself should give you the hint. Inductance by definition is the ratio of flux to current. Okay. So if current changes, flux changes, and if flux changes according to Faraday's law, there will be an EMF induced which will oppose the change in flux, means it opposes the change in current. So inductor does not allow the current to grow suddenly. Fine. So if you directly connect the plates of a charged capacitor, they'll discharge immediately. Okay, producing a high amount of current, usually leading to a spark. But if you connect the plates of a capacitor through an inductor won't allow the current to increase suddenly, so the charge will gradually decrease. Fine. But what happens? Inductor opposes the change in current, no? Current tends to increase. Before the switch is closed, current is zero. After the switch is closed, current suddenly wants to become a large value, but an inductor does not allow that. Okay, it's like creating an opposing force actually to the current. So what we can do now is write an equation for current as a function of time or charge on the capacitor as a function of time. The charge is not going to get neutralized immediately. It will take time. So we have to derive an equation for it. Let us do that. This is the circuit that we are considering. Assume the switch is closed at t equal to 0. After you close the switch at a random instant, the situation will be like this. So you can say at time t, okay, some random instant t, when the switch is closed, there will be a current flowing this way. The charge would have changed. Okay, so let's consider a random charge small q on this plate minus small q on the other plate, and the current is I. We need an equation for the charge or an equation for the current. One of you recollect and tell me, be it the charging equation of a capacitor, discharging equation, or growth of current in an inductor, or decay of current in an inductor, whatever it is, how do we write current equations in such situations? What concept do we apply to get the current equation or the charge equation? Okay. Tell me, what are the basics we can apply in electricity? What are the basic equations that we apply in electricity? I mean,
Sir, we can do KVL over here.
correct. KVL. Okay. So what we are going to do is we will start maybe from this point and move clockwise. First, we are moving across the inductor. Isha, tell me, how do we write potential change across an inductor?
Minus LDI by dt.
Correct. Minus L di by dt if you are going in the direction of current. Correct. That's how we are going. And Rishi, you tell me, how do we write potential change across a capacitor?
Sir, minus Q by C.
No, it's not like a formula minus Q by C. Isha, you tell.
Minus of minus Q by C.
It's negative of charge on the first plate that you come across divided by C. Here, the first plate of the capacitor which we encounter is having a charge minus Q. So it becomes minus of minus Q by C. Rishi, is this clear?
Yes, sir.
And since we return to the starting point, this should be equal to 0. So basically, potential change across the inductor plus potential change across the capacitor is being equated to 0, KVL. Okay. Minus of minus becomes plus. Keep it this side, send LDI by dt that side. So you get Q by C is equal to L di by dt. Now in this situation, after you close the switch, okay, it's like the two plates have been connected, but they have been connected through an inductor, not directly. So charge will change. You know, charge will slowly decrease, and current also will change. Inductor doesn't allow current. It provides some opposition to current, but the current will keep changing. It will increase anyway. So Q is a variable, I is also a variable. So there are two variables in this equation. Of course, three. Time is anyway a variable. So there are three variables in this equation. We'll have to convert it to two variable equation. One of you tell me, how is current related to charge? How is current related to charge? I is equal to dq by dt. That's the definition of current. Okay, Pradyun. Don't say q by t. Q by t is for 10th class. Okay, now in plus 2, you should at least say dq by dt. That's the definition of current. Now you all look at the circuit. One plate is positively charged. The other plate of the capacitor is negatively charged. When you close the switch, electrons will flow this way from positive to negative. That means the current flows, electrons will flow from negative to positive. That means the current flows from positive to negative like this. Now, if current actually flows like this, suppose the current is positive, one of you tell me what happens to the charge on the positive plate? Does it increase or decrease if current actually flows like this? Will the charge on the positive plate increase or decrease? We have assumed current to be flowing clockwise. If that is actually what is happening, what happens to charge on the positive plate, left side plate? Pradyun, what do you think? Does that positive Q increase or decrease due to this current? Okay, you gave answer as increase. Rishi, what do you say?
Sir, I think it'll be increased only.
How can you can you justify that?
Sir, because electric current goes in like the
Hmm.
uh, because electrons go in the opposite side, the positive charge flows towards the part of in the direction of the current. So, and it's going.
Positive charge is going in the direction of current. So what happens to the charge on the plate of the capacitor is what I'm asking. How does it increase? You are saying it flows off, it flows out. Then how will the charge on the plate increase? Okay, let me consider, let me show you a capacitor like this. Assume there's a switch connecting the plates directly. Assume there's a charge of +2 microcoulombs on this plate and -2 microcoulombs on this plate. Close the switch. What happens to this charge? Will it stay +2? Will it become more than +2 or will it become less than +2? Isha, what do you say?
Sir, it'll decrease, sir.
It will decrease. Okay. Basically, the charges neutralize. Neutralize means they'll tend to become zero. So +2 going to 0 means it has to decrease only, no? And to decrease, electrons will have to come this way. If electrons are coming this way, it means the current is flowing like this. So if current flows clockwise, the charge on the left side plate will decrease. Current is the rate of flow of charge, okay? Okay. So current tells you how quickly the charge is moving. But the charge is going out of the plate, not into the plate. So the charge left on the plate will decrease. So if you want to relate this current to this charge Q, then you should write I is minus dq by dt. Because due to this current, the charge Q will decrease. So here I becomes minus dq by dt. And if I is minus dq by dt, then derivative of I will be minus second derivative of charge d square q by dt square. Therefore, the KVL equation changes to q by c is equal to minus L d square q by dt square. And we can rearrange this equation as d square q by dt square, second derivative of charge, is minus 1 by LC into q. I'm sending the L to the other side and the minus also. Okay. So if a charged capacitor is being discharged through an inductor, this is the equation for charge as a function of time. We have not solved the equation yet. We got a second order differential equation. Okay. Do any of you know how to solve such equations? I don't know if you have second order differential equations in your syllabus or not, but do you know how to solve this? D square y by dx square is equal to minus some constant into x. Can you solve this equation? Okay. I'll just give you a quick review. You all must have definitely come across an equation like this in simple harmonic motion. Okay, can any of you, if you remember, okay, tell me what is the basic condition for linear SHM? What kind of force produces linear simple harmonic motion?
Sir, the Force on the acceleration should be directly proportional to the object's display.
Okay, continue. Force and acceleration should be directly proportional to objects.
Displacement.
Okay, fine, correct. And the direction should be, I mean, magnitude wise, they should be proportional. See, if force is proportional to displacement, automatically acceleration will be proportional to displacement, because according to Newton's second law, F net equal to ma. Okay, so force or acceleration should be proportional to displacement from the mean position, and the direction should be opposite to the displacement. Direction of force should be opposite to displacement. So let me quickly review that. The force which can make an object undergo simple harmonic motion should be of this form: F is equal to minus kx, where F is the net force acting on the object, x is the displacement of the object from mean position. Okay, mean position is the position where net force is 0. Let it be. And we know F net equal to ma, so you get acceleration is minus k by m into x. Okay, k is proportionality constant between force and displacement. In spring block systems, k will be the spring constant. In some other cases, it will be something else, but it's a constant between force and displacement. Divided by mass of the object. Mass is constant anyway. Okay, so k by m will be a constant. We call that, okay, we can write this equation. Acceleration is second derivative of displacement. First derivative of displacement is velocity. Differentiate it again, you get acceleration. So you get acceleration is minus some constant. That constant I'll write as omega square into x. This is the basic condition for SHM. Linear simple harmonic motion of an object. Okay. The equation we have here for charge on the capacitor when it is being discharged through an inductor is somewhat similar to this. Okay, you can observe the similarity directly. There x represents displacement from mean position. Here we have q in place of x, where q is the charge on the capacitor. And in place of omega square in linear SHM, here we have 1 by LC. Let's call 1 by LC as omega square. That means omega is 1 by under root LC. Let's take it like that. And in linear SHM, we actually solve this equation and get x as a function of time. How we solve? We know d square x by dt square is acceleration, no? So acceleration is minus omega square x. And by definition, acceleration is v dv by dx. Okay, so you get v dv is equal to minus omega square x dx. Integrate both sides, you will get velocity in terms of x. Okay, once you get velocity in terms of x, I'm not actually going to do all that. Once you get velocity in terms of x, you equate it to dx by dt, because velocity by definition is rate of change of position with respect to time. You equate it to dx by dt, then keep all the x terms on one side, t terms on the other side, integrate once again. You will finally get an equation like this: x is equal to a sine omega t plus phi. Okay, this is the solution to this second order differential equation. Okay, this is the differential equation in terms of x and time. And for that, the proper equation which satisfies that differential equation is this. X is equal to a sine omega t plus phi, where we call a as amplitude of oscillation. Omega is called angular frequency, phi is called phase constant, all those things you know. Now, what do we mean by amplitude of oscillation? Amplitude is nothing but maximum displacement away from the mean position. Okay, because x itself means displacement, a is the maximum value of x. So that's the maximum displacement away from mean position. Now look at the differential equation that we have here. For charge on the capacitor, we have d square q by dt square, that's the second derivative of charge, is minus omega square into q. Now for d square x by dt square is minus omega square into x. If this is the solution, then for d square q by dt square is minus omega square into q should have or will have a solution like this. In place of x, you have the charge on the capacitor. And A is displacement amplitude, the maximum displacement away from the mean position. For charge, you'll have the maximum charge that the capacitor plate can store. That's all. The rest of the equation remains the same. Therefore, you get charge on the capacitor plate as Q naught sine omega t plus phi. And we have been discussing alternating EMF, alternating current since 5-6 classes. Okay, I think 8 classes. We know that this is an alternating function. It varies from -1 to +1. If this function varies from -1 to +1, then the entire charge on the plate of the capacitor keeps varying from minus Q naught to plus Q naught. Okay, this is what is interesting. So the moment you close this switch and allow the charges to combine, okay, in this LC circuit, when you close the switch and allow the charges to combine, what happens is the charges don't simply combine and become zero. By the time the charges combine, no, see, assume the switch is closed. You have to visualize it like this. Imagine positive charge going from one side, negative charge coming from the other side. They'll combine somewhere. But till then, they would have accelerated, no? Positive charge and negative charge. You can think of it this way. Let's say there's a plus Q here and there's a minus Q here. You leave them, you know they'll combine. But as they come close to each other, their speeds will increase. They'll have inertia. Fine. So you have to imagine it like this. When they come close to each other, they have a lot of speed. They cross over and go to the other side. Okay. If you visualize it like that, then you'll be able to understand LC oscillation better. Okay. So what happens? The minus Q is initially on the right plate. Let's call the plates of the capacitor as A and B. A is positively charged, B is negatively charged. But when you allow them to combine, no, what will happen? The minus Q will come to this side, plus Q will go to that side due to inertia. And then they'll combine again, reverse. Okay, like minus Q on the left plate, plus Q on the right plate. They'll attract each other, they'll try to combine again, but they'll switch places once again. So they'll keep going back and forth like this. That is what is called LC oscillation. The charge oscillates in the circuit. It goes back and forth. And that is what this equation also suggests. You get Q is equal to Q naught sine omega t plus phi. You know this is an oscillating function with an amplitude of Q naught, means maximum value of Q naught. So for some time, the left plate will have a charge plus Q naught. Then it will gradually decrease, become 0, and then go to negative. It will go to minus Q naught also. Again, it goes back to plus Q naught. It keeps oscillating back and forth. And you know, an inductor or a capacitor do not dissipate energy. Resistors dissipate energy. Now, this capacitor was initially charged. Fine. And we have not considered any resistance anywhere if you observe. Now, some of you may say, sir, charges when they neutralize, they'll lose all that energy. Where will the energy go? It should get dissipated as heat. The charges should come to rest. No, they should undergo collisions and come to rest. Undergoing collisions means resistance. But there's no resistance in the circuit. We considered ideal inductor, ideal capacitor. Okay, that is why I said when they try to combine, no, they don't stop. Due to inertia, they go to the other side. There are no collisions happening. Basically, that is the situation. Okay, in an LC circuit, there are no collision of charges with anything. So because there's no resistance. Okay, so when the charges try to combine, they don't simply stop. They cross over to the other side. Minus Q and plus Q switch places. They'll again try to combine. They'll again switch places, and that will keep happening forever. If there is a resistance, no, gradually heat will get dissipated, energy will get dissipated, the charges will slow down, and finally the current will become 0. Charge movement will stop. LC oscillation will stop, but there's no resistance here. Okay. In fact, we can extend this discussion a little further also. In 11th, you must have studied damped oscillator. Okay, in oscillations itself, there's something called damped oscillations and forced oscillations. Forces like friction, air resistance, they decrease the amplitude of oscillation and finally make it stop. Similarly, in an electrical circuit like this, resistance does that work. It will slowly decrease the amplitude of oscillation of charge, and it will finally stop the charge from moving. Okay, but anyway, for now, we'll not consider that. So we get charge as a function of time like this. That is why, I mean, it's an oscillating charge. That is why it's called LC oscillation. And if this is charge as a function of time, differentiating this should give us current as a function of time. But we know in this circuit, I is actually minus dq by dt. So minus of derivative of the charge function. Q naught stays as it is. Sine derivative is cos omega t plus phi. You'll have to multiply it with omega. Okay. So the current becomes minus Q naught omega cos omega t plus phi. And Q naught omega becomes the peak value of current, I naught. So you see that the current is also an oscillating function. Current increases, decreases, increases, like it flows this way for some time, then the other way. So for half cycle current is positive, and for half cycle current will be negative. Okay. In fact, if you visualize the proper graph of this equation, it's a cos function minus cos function, let it be. You know, cos function starts from plus 1. Here it's negative, so let's start it from minus 1. Then the current will keep oscillating like this. There are a lot of interesting things that you need to observe here. Current is initially negative, that's fine. It just means anti-clockwise current or clockwise current. Let it be. Plus or minus depends on which direction you consider positive. But initially current is high, decreases to 0, then increases to a maximum on the other side, means reverse direction. So initially you can imagine there is a lot of current, high amount of current, slowly decreases, becomes 0. That's when the charges have switched places. But now they'll have to come back. So the current will have to increase in the opposite direction now. It increases, decreases. So it increases and comes down to 0 again. That's when they have completed switching places. But now they'll have to go back again. So current flows in the reverse direction, increases, decreases, becomes 0. Okay, so as the charges keep switching places, current keeps increasing and decreasing in that process. Okay. And one more thing, when the charges have fully switched places, current becomes 0. Then current in the reverse direction will start. When the charges have fully switched places, that means the charge on the capacitor is maximum. At that moment, how much is the current? 0. When the charges are in the process of shifting places, switching places, current is non-zero. But once they have completely switched places, current becomes 0. So when the capacitor is fully charged, current is 0. When the capacitor is getting discharged, current is non-zero. Okay, you can observe that in the equations also. The charge function we got is Q equal to Q naught sine omega t plus phi. Let it be. The corresponding current function we got is minus Q naught omega. I'll take it as I naught cos. Now minus cos theta, how can you write it as sine of something? Can one of you tell me? How to write minus cos theta as sine of something?
So 90 minus theta.
Okay, you are saying sine 90 minus theta. 90 minus theta will fall in the first quadrant only, and sine 90 minus theta is simply cos theta. It's not minus cos theta. But you're very close to the answer. You have to make it negative. How to make the sine function negative?
So cos 90 plus theta is minus sine theta.
Okay, cos of 90 plus theta is minus sine theta. That is correct only. But what will you take
Is
inside
it
the...
sine 180? Is it sine 180 plus theta?
See, if you put 180 inside the bracket, no, the function does not change. Plus minus can change, but sine stays sine.
Oh yeah, sir.
You have to do something with 90 only. Isha, sine of what can be taken as minus cos theta?
Is it theta minus 90?
That's all. Huh. Okay. Sine 90 degree minus theta is cos theta. This is a well-known identity. And if you put a minus inside the sign bracket, no, that minus can be taken out. So you can say we want minus on both sides. We want minus cos theta actually. So we'll put a minus here. Send the minus inside. Then what does it become? Sine of theta minus 90 is minus cos theta. Okay. So the current function we derived is minus cos something. We can write it as Q naught omega. I'm writing it as I naught, peak current. Sine of, what do you have inside the cos bracket? Omega t plus phi. That is theta minus pi by 2. And what is the intention behind doing this? We have to get both charge and current in terms of the same function so that we can compare the phases of these equations. The phase of the charge equation is omega t plus phi. Whatever is inside the sine or cos bracket is what we call as phase. Okay. Omega t plus phi is the phase of the charge function. Omega t plus phi minus pi by 2 is the phase of the current function. One of you tell me directly, what is the phase difference between them? Phase difference between charge and current. Obviously, you can just see and tell it is pi by 2. Pi by 2 means 1/4 of a cycle. 2 pi is one full cycle. Pi is half cycle. Pi by 2 is 1/4 of a cycle. So charge function, as you can see, is ahead of the current function by a phase of pi by 2. Or you can say current is behind the charge function by a phase difference of pi by 2. Means when charge is 0, current will be negative extreme, like minus I naught. Then when charge goes to positive extreme, current comes to 0. So basically, when one is at the extreme, the other will be at the mean, means 0. And that's what we have discussed also. When the charges have completed switching places, current becomes 0. Charges have completed switching places means the capacitor is again fully charged. There's no charge moving in the wires. They have switched places completely. So capacitor is fully charged. At that time, the current is 0. So when charge is maximum, current is 0. That is what we mean by having a phase difference of pi by 2 or 1/4 of a cycle. Okay. When current is maximum, charge will be 0. Okay, that case is also there. See, the charges plus Q and minus Q, they switch places, no? In that process, there will come one instant. Okay, let me copy the circuit. As the plus Q and minus Q switch places, there will be one instant when this happens. The charge on the capacitor will totally become 0. Okay, they're in the process of exchanging places. So they're on the way, you can say. All the charge has left the plates. It's in the process of switching places. In that case, the current will be the peak current. Highest amount of current will be flowing at that time. And there's another way also to look at this. Initially, capacitor was charged. Means capacitor had energy. What kind of energy does a capacitor store? Can one of you tell me? What kind of energy does a capacitor store? Rishi, don't answer. Others, respond. Isha, what kind of energy does a capacitor store? Yashmit,
Sir, isn't it just potential energy?
no.
I don't remember actually. It's
Okay.
been a long time.
Okay. Capacitor stores electrical energy. Inductor can store magnetic energy. Simple. And capacitor stores electrical energy in the electric field between its plates. Okay. So initially, when like before closing the switch, the capacitor was charged. It had energy with it. Now you know charge will exchange place, like charges will try to switch places. We have derived that. In that process, there will be one instant when there is no charge at all on the capacitor. All the charge is in the process of getting transferred. Okay. When there's no charge on the capacitor, the energy stored in the capacitor becomes zero. But where will the energy go? Energy cannot get dissipated here. There's no resistance. Capacitor has lost its energy. At that moment, inductor will be having the energy. Okay, whatever energy the capacitor is losing gets stored in the inductor, in the magnetic field of the inductor. Okay, so as the capacitor gets discharged, energy of the capacitor will decrease. But in the process, as the capacitor gets discharged, current will be increasing. Our charge decreases, current increases. Okay, when charge is maximum, current is zero. But from maximum, as the charge is coming down, current will be going up. So charge is coming down means energy in the capacitor is coming down. But at the same time, current is increasing means energy in the inductor will be increasing. They will transfer, the energy gets transferred from capacitor to inductor. And then the reverse will happen. When current is maximum, inductor stores all the energy, charge will be zero, no energy with the capacitor. But you know it's a cycle that keeps happening. We have derived the equation. It's an oscillating charge, it's an oscillating current. From the peak value, current will again come down to zero. As the current comes down to zero, charge will again go to the extreme value. When current is coming down to zero, inductor is losing its energy, but in that process, capacitor is getting charged. So capacitor is gaining the energy. So in an LC oscillation or in an LC oscillator, the capacitor and the inductor keep exchanging the energy. When the capacitor has lost all its energy, inductor has maximum amount of energy, obviously. Okay. When the inductor loses all its energy, capacitor will have maximum amount of energy. Okay. So it's somewhat like a spring block system actually. Let me take one diagram, just a moment. Okay, we'll consider this. You imagine a spring block system oscillating on a smooth horizontal surface. Just a moment, I'll make some adjustments. Consider it like this. Assume the spring is compressed. Okay. Let's say this is the natural or the relaxed length of the spring. You compress the spring and release the block from rest. When the block is at rest, kinetic energy is zero. But the spring is compressed means it will have potential energy, and it's compressed to the maximum extent, so maximum potential energy. So at this position, kinetic energy is zero, potential energy is maximum. Okay, spring stores elastic potential energy. Now, when you release this, what will happen? The spring relaxes. And as the spring relaxes, it pushes the block. So what happens is the block moves to the right. Assume the block goes all the way to the natural length. Okay, let's say the spring has relaxed all the way to the natural length. Think of it like this. When spring is relaxed, there's no potential energy in the spring. Potential energy is zero at this position. But till then, the block would have been pushed. So the block has a lot of speed here. It has the highest amount of speed actually that it can get. So the kinetic energy is maximum. So potential energy gets converted to kinetic energy as the spring relaxes. Now the block has some speed here. It has inertia. Then it will go to the other side. Like charge is going back and forth in an LC circuit, the block goes back and forth in a spring block system. Okay, actually we have to look at it in the reverse manner. When just like a spring block system oscillates, the charge oscillates in an LC oscillator. So after some time, you'll see the block coming to this position. There the spring will be extended to the stretched to the maximum extent. There the kinetic energy of the block becomes 0. Potential energy will be maximum again. Okay, so energy keeps getting converted between potential and kinetic in a spring block system. Something similar happens in an LC oscillator. Energy keeps getting converted from electrical to magnetic and back from magnetic to electrical. Okay, and now we will do the calculation part. Remember, if you want to find out how much energy is there on the capacitor or how much energy is there in the inductor, you will need these equations, because energy stored in a capacitor depends on charge on the capacitor. Energy stored in an inductor depends on current flowing through the inductor, half Li square. Okay, so let's do that. Consider a system like this. Okay, see, we already have the charge equation in this particular case only we derived. So if you close the switch at t equal to 0, then charge as a function of time, I should write small q, charge on the left plate of the capacitor as a function of time will be initial charge q naught sine omega t plus phi. When t equal to 0, the left plate had the charge q naught on it. Okay, so when t is 0, the charge should be equal to q naught. So left hand side is q naught, right hand side should also be q naught, means this part should become 1. This should become 1 means the phase constant here should be pi by 2, because sine pi by 2 is 1. Therefore, the charge equation is actually q naught sine omega t plus pi by 2. The phase constant is pi by 2. Based on the initial conditions, we can find out the phase constant. And from this, we know the current equation, q naught into omega. Q naught omega, I naught is q naught omega, sine charge phase minus pi by 2. Okay, then the current equation can be written like this. Q naught omega sine phase of the charge minus pi by 2. If you subtract pi by 2, that pi by 2 gets cancelled. You'll only be left with omega t. So these are the charge and current functions in terms of time. Charge and current equations in terms of time. If you want to substitute t as 0, if you put t as 0, charge will be q naught, current will be 0. Maximum charge, 0 current. And you can find out charge and current at any time using this equation. Okay. First thing, what is the time period of oscillation? This is very easy, direct. Next, at time 1/4 of the time period of oscillation, how much is the charge on the capacitor and how much is the current in the circuit? That's the second part. Then third part, at t is equal to, let's say, 1/6 of time period. How much is the charge on the capacitor and how much is the current in the circuit? Solve all these. Can one of you tell me the time period of oscillation of these functions, this one or this one? What is the time period of the function sine omega t?
2 pi by omega.
2 pi by omega, that's all. Okay. Answer the remaining questions. Okay. Any answer for charge at t naught by 4? You just have to substitute in the equation.
Sir, q naught sine 5 pi by 2.
Rishi, I won't do the calculation. You have to do. And okay, how did you get 5 pi by 2? I asked you to take the
Sir,
time as t naught by 4. Okay. T naught by 4. T naught is 2 pi by omega. If you divide that by 4, it becomes pi by 2 omega. Okay. So this is the time of pi by 2 omega. We'll substitute that in the charge function, charge equation. Others, any answer for charge at that time? Isha? I want you all to do this is easy only. Just put this
sir,
time pi by 2 omega there.
sir, so is the answer not Q naught sine phi pi by 2?
No, I don't think you'll get 5.
Sir, because T naught is 2 pi by omega, and then T is equal to 1 by 4. And then the equation will become Q naught sine
Wait,
omega
let me write. Q naught sine, continue.
Omega into 2 pi by pi plus pi by 2.
2 omega into,
2 pi by omega.
see, what is T naught? What is the meaning of T naught?
Time period, sir.
Time period. That's the time taken to complete one cycle. And what is T here in this equation?
T.
Time at that instant. That T is not time period, okay? Time period is a fixed value. This small t is a variable time. It keeps increasing. So when small t is equal to T naught by 4, I asked you to find out the charge. So you will put this in place of small t, no? That's the time.
Oh, yeah, sir.
Huh?
1
Okay.
minute, sir. I'll solve.
Fine. Others also. Pradyun, Isha, solve it and come up with some answer. It's easy only. You just have to substitute the time pi by 2 omega there. And then simplify the sine function. Okay. Anyone? How much is the charge at that instant? Time is pi by 2 omega. You put it there.
Sir, Q naught sine 3 pi by 2.
How did 3 come? Like, how did you get the 3? Omegas will get
Because
cancelled.
3 pi by 2 omega.
That's what. How
3
did it
pi.
Not
become?
sine pi.
Okay, it's Q naught sine pi. See, when you substitute the time as pi by 2 omega, the omegas get cancelled. You'll be left with a pi by 2 plus a pi by 2. Pi by 2 plus pi by 2 is pi. Okay. And sine pi is sine 180 degrees. That is 0. So at this time, the charge on the capacitor is 0. Let it be. Let's find out the current now. Okay, the second part we'll solve later. At least current, derive it on your own, all of you. The current equation we got is this: Q naught omega sine omega t. Substitute the time in this and tell me how much is the current. Tell directly, you don't even have to use pen. Rishi, in place of t, small t, if you now substitute pi by 2 omega, what will be left inside the bracket after simplification?
Pi by 2, sir.
Pi by 2. How much is sine pi by 2?
1.
1. Sine pi by 2, sine 90 degrees is 1. Then how much does the current become?
Q naught omega only.
Then current becomes Q naught omega. This is basically the peak current. Okay, so this is what I was telling you. When the capacitor loses all its charge, current will be at the highest value. Current will be maximum. Okay, the charge is in the process of switching place. The charge has left the plates completely. Then there'll be maximum rate of transfer. Current will be maximum. And if current is maximum, automatically the energy stored in the inductor will be maximum. So capacitor has lost all its energy, charge became zero. Inductor has taken all that energy. Okay, in fact, we can prove also that the energy lost by the capacitor is equal to energy gained by inductor. Let us do that. One of you quickly tell me the formula for energy stored on a capacitor, stored in a capacitor in terms of charge. In terms of charge, what is the formula for energy stored in a capacitor?
Half CV square, sir.
Yeah, where is charge in that equation? Rishi, come on. Half
Yeah,
CV square. Isha, what is the formula for energy stored in a capacitor in terms of charge?
sir, half QV.
QV by 2.
Like,
Okay, okay. Reasonable. But here we know the capacitance, C. So in terms of Q and C, can any of you tell me the formula? In terms of Q and C.
Q square by 2C.
Okay, Q square by 2C. So at that time, okay, this is the formula for energy stored on capacitor. What is the energy stored in an inductor? Formula. For this, luckily, there's only one formula. Tell me that one formula, please. Energy stored in an inductor. I think I'll have to make you write these
half Li
formulas
square, sir.
50 times. Okay. Half Li square. Okay. Now at the time that you were asked, that is 1/4 of the time period, you got charge as 0 and you got current as peak current Q naught omega. Okay. Therefore, energy stored in the capacitor will be 0. Q square by 2C becomes 0. In fact, you have to take small q, charge at particular instant. And energy stored in the inductor will be half L square the current. It becomes Q naught square omega square. Okay. And omega we know is 1 by root LC. In LC oscillations, omega is 1 by root LC. So omega square becomes 1 by LC. L gets cancelled. You get Q naught square by 2C. That's the energy stored in the inductor now. But this Q naught square by 2C was with the capacitor initially, when capacitor had all the charge. So this is proof that all the energy stored in the capacitor comes to the inductor at one point. Okay. And it will again go back to the capacitor. They'll keep exchanging that energy, transferring that energy between themselves. Okay. Now solve the other part that was given to you. If you want, I'll give you these charge and current equations. We know time period also. Time period is 2 pi by omega. What was the second question that I asked you? In the second question, you were asked at the time t is equal to 1/6 of time period. Okay. How much is the charge? How much is the current? And if you know charge and current, you can tell energy stored in the capacitor. You can tell energy stored in the inductor also. Do this, all of you. Substitute carefully. These are very basic calculations that we are doing. You substitute the given time, the charge you get will be Q naught sine. Time is pi by 3 omega. Omega gets cancelled. Pi by 3 plus pi by 2. Pi by 2 is like 90 degrees. Rishi, how did this become 0? You answered 0.
Yeah,
What is
sir, calculation.
okay, now you tell me, what is sine theta plus 90 equal to? Anyone? Sine theta plus 90?
Sir, cos theta.
Okay. See, I'm interacting more with him because he is coming out with the first answer. Okay. If any others answer, then I'll ask more questions to you also. Fine. Sin theta plus 90 is cos theta. So this effectively becomes Q naught cos pi by 3. Pi by 3 is 60 degrees. Cos 60 is 1 by 2. So Q naught cos 60 becomes Q naught by 2. Therefore, we can say that the capacitor has lost half its charge. Means half the charge has left the plates of the capacitor and is in the process of getting transferred. Switching place. Okay. That's the charge at that moment. Next, current. Directly substitute the time that you are given here. Pi by 3 omega. Omega gets cancelled. Sin pi by 3. Sin 60 degrees is root 3 by 2. So the current becomes root 3 Q naught omega by 2. Okay. So charge has not gone to 0 all the way. So current also has not reached its peak value. It's root 3 by 2 times of the peak value. It still did not become maximum. So charge is in the process of decreasing. Okay, yeah, 1/6 of the time period. No, yeah, charge is in the process of decreasing. Current is in the process of increasing. Okay, next, energy stored in the capacitor, energy stored in inductor. Capacitor formula is Q square by 2C, but the charge at this moment is only half of the initial charge. So we'll have to square that only. So Q naught by 2 whole square by 2C effectively becomes 1 by 2 whole square is 1 by 4 by 2 is 1 by 8. Q naught square by 8C. That's the energy stored in the capacitor at that moment. Okay. Energy stored in the inductor, half L I square, half L, square the current. Root 3 by 2, if you square it, it becomes 3 by 4. And Q naught omega, if you square, it becomes Q naught square, omega square. Omega square is 1 by LC, I'm writing it directly. L gets cancelled. You will be left with 3 Q naught square by 8C. And observe, there's some energy on the capacitor, there's some energy on the inductor. Initially, means when we just closed the switch in the circuit, all the energy was with the capacitor. How much? It had Q naught square by 2C, full energy. Inductor had 0 because initially when the switch was open, there was no current. Inductor didn't have any energy with it. Okay, so the total energy in this circuit is Q naught square by 2C, all of which was with the capacitor initially. Now see, at this time, pi by 6 omega, sorry, T naught by 6, that is pi by 3 omega, capacitor only has some energy. It doesn't have Q naught square by 2C. It only has Q naught square by 8C. And the inductor has the remaining energy. Let us add these two. Energy on capacitor plus energy on inductor. You get 1 by 8 plus 3 by 8 times of Q naught square by C. 1 by 8 plus 3 by 8 is 4 by 8. That is nothing but 1 by 2. So effectively it becomes Q naught square by 2C. And it makes complete sense. The sum of energy on the capacitor and the inductor should be equal to the total energy in the circuit. And the total energy in the circuit we found out from the initial condition, it was Q naught square by 2C only. Capacitor was having all that energy. Now what happened at that time of 1/6 of time period, that is pi by 3 omega, some energy went from capacitor to the inductor. But the sum, but the addition of those energies still remains the same. Okay, so this is what actually happens in an LC oscillation circuit. Capacitor inductor keep exchanging energy between themselves. But the sum of the energies stored in the capacitor inductor will always be the same. That's the total energy in the circuit. There will be some instance when all that energy is with the capacitor and nothing is with the inductor. There will also be some instance when all the energy is with the inductor, nothing with the capacitor. And there will be some instance where they are sharing the energy. Some with capacitor, some with inductor. Okay, so by solving KVL equation, you can write current as a function of time, charge as function of time. That's what we have done in the last two questions. Based on charge and current at a particular time, you can even tell the energies. Now, usually in LC oscillation, they tend to ask direct questions. What kind of direct questions? Consider an LC oscillator. Okay, they won't even draw the diagram. They'll just say something like this. In an LC oscillator, let's say initial charge is Q naught. And initial current is 0. Means initially capacitor had all the energy. Okay, that they won't say that. First question. Calculate maximum current in the circuit. Okay, L and C are given to you. L and C are given, initial charge Q naught is given. Calculate maximum current in the circuit, that's the first part. Second part, calculate charge on the capacitor when energy, they keep exchanging energy. There will be one instant when capacitor stores the equal amount of energy as the inductor. Okay, see, from capacitor it goes to the inductor, but in that process of going, at one instant they'll have equal amount of energy. So calculate the charge on the capacitor when energy is equally distributed. Between inductor and capacitor. Okay, try these two. Can one of you tell me an idea to calculate the maximum current? Okay, Isha, initially capacitor is charged, there was no current. Can you tell me what happens after that, after the switch is closed? No response. Rishi, can you tell? Charged capacitor is connected to an inductor and the system is left on its own. What will happen?
The current will flow through it until the charge is zero.
Until the charge is?
Like the charge neutralizes itself, and like
After that, what will happen? Current will stop? In an
no,
LC,
it'll keep flowing.
it'll keep oscillating. Actually, when the charge is completely neutralized, no, we should not say neutralized also. When the charge on the capacitor is 0, current will be maximum. That's when charge transfer will be happening at its highest rate. All charge has left the plate of the capacitor, but transfer is happening. Anyway, so yeah, that is what happens. As charge decreases, current increases. When charge comes down to 0, current will be maximum. And the question is asking you that only. Calculate the maximum current. Now charge has become 0. At that time, current has become maximum. We have to calculate how much that maximum current is. If you remember the equations, you can do it. One of you, just recollect the equations that we derived today. What was the expression for peak current?
So Q naught omega sine omega t.
That is the current equation. How much is the peak current maximum? Rishi, what you said is the current equation. What is the maximum value of that equation?
Q naught omega.
Q naught omega, correct. And how much is omega in an LC circuit? Because in the question, omega is not given. In an LC oscillator, what is omega equal to? Okay, go through the derivation once. Since you have derived it today itself, you may not remember. But omega in the original derivation is 1 by root LC. The proportionality constant between second derivative of charge and the charge itself is what we call omega square. 1 by LC is omega square, so omega is 1 by root LC. Don't forget this. So if L and C are known, it's like omega is known to you. And if omega is known and the peak charge is known, peak current becomes Q naught into omega. that is Q naught by under root LC. You can answer it like this. There is another way also to answer, to find out the maximum current. When current is maximum, we know charge on the capacitor will be 0. Means all the energy must have gotten transferred from capacitor to the inductor. That is the instant when current is maximum. Okay. Initially, capacitor has a charge Q naught. Therefore, energy in the circuit, that is capacitor plus inductor energy, is Q naught square by 2C on the capacitor plus nothing on the inductor. This is the initial situation. When current is maximum, what happens is you will see nothing on the capacitor. You will see all energy with the inductor. That's when the current is maximum. So I'm writing I naught and squaring it. So if you equate these two, 2's will get cancelled. You get I naught square is equal to Q naught square by LC, or you get I naught is equal to Q naught by under root LC. That is nothing but Q naught omega. Okay. But remember, you can look at it this way also. The question was asking you what is the maximum current. So the idea we used is when current is maximum, all the energy will be with the inductor. But earlier all the energy was with the capacitor. So what we are doing is earlier energy stored in the capacitor equal to current energy stored in the inductor. That means at present what energy is stored in the inductor. That's all. From that you will get at present what current is flowing, and that itself is the maximum current. So you can rely on the equation that we derived, or you can use this idea that energy is getting transferred to the inductor. Okay, solve the second part at least. You are asked to calculate the charge on the capacitor when energy is equally distributed between inductor and capacitor. Initially, all the energy was with the capacitor. Okay, let me help you out a little bit. Initial energy stored in capacitor, energy stored in inductor. Final, okay. Initially, capacitor had Q naught square by 2C, inductor didn't have any energy. Finally, we don't know, but we know that it should be half and half, equally distributed. So let this be U and this be U. We don't know how much U is, you can find out. Okay. So final means at the instant that you are asked about, the energy is equally distributed. And at that moment, you are asked to find out the charge on the capacitor. Okay. Try this.
Sir, so I don't know if it's like the correct approach, but so since they've given like the total charge for the capacitor as like maximum as Q naught square by 2C,
That's the
we
maximum
divide
energy.
that. Yeah, we divide that into half for the capacitor for 1
Correct.
U, which will become Q naught square by C.
Half of Q naught square by 2C is
No,
Q naught square by
yeah,
4C.
no, sir, my bad.
Okay, okay.
Q
After
naught
that,
square
what
by
will you do? You know the energy stored
yes,
on the
sir.
capacitor. What was the question? What did you actually have to find out?
The charge.
Charge. Okay, try to do that. Isha, Pradyun, any answer? Charge when the energy is equally distributed. See, energy is equally distributed. Based on that fact, we found out how much energy is with the capacitor, how much is with the inductor. If you know how much energy a capacitor has, can't you tell how much charge it has? This is easy only. Come on. So based on energy, you equate it to charge on the capacitor square divided by 2C. That's all. You'll get Q is equal to Q naught by root 2. That's the charge at that moment. You can even tell what is the current at that moment. Equate it to half Li square. You can tell how much current is flowing at that instant.
So we just substitute it with the normal formula of the QC
That's
bar.
all. That's all. What else will you do? You know the energy. Based on that, you have to tell the charge. Use the formula for energy in terms of charge. Okay. So in this question, I asked to find out the charge when when the energy is equally distributed. They may even ask you to find out the charge on the capacitor when energy is distributed in the ratio 1:3. So they can give you ratio. Split it according to that ratio. And based on energy in capacitor, you tell the charge. Based on energy in inductor, you tell the current. Simple. Okay. So the questions need not always be answered based on the charge equation or the current equation. Just by knowing energies also, you can tell how much is the charge, how much is the current. Fine. So, okay, that is all you need to know about LC oscillation. There are different ways of writing the equation. I'll send you a worksheet tomorrow based on all this. And tomorrow itself, I'll take a short class, maybe half an hour. We'll finish off transformers. Okay. So that day after tomorrow in our usual class, we can start, what is that? Electromagnetic waves. EM waves is a small chapter. And I'll tell you what all you need to know. For EM waves, to understand EM waves chapter properly, you need to know the general wave equation. Okay. General wave equation goes like this. In 11th class waves chapter, you would have studied y is equal to a sine kx plus or minus omega t plus phi. So if you are given a wave equation like this, you should be able to tell which way the wave is traveling. So direction. You should be able to tell speed of the wave, frequency of the wave, wavelength of the wave from a general wave equation. Just revise that part. Okay, fine. We'll stop it here. Pradyumna has sent me one question. We'll discuss that.